All right. Ladies and gentlemen, class recording has started. So anything you do from this point on might be able to get heard. Okay, so keep it under control. All right. Where we want to go today is we want to introduce this idea of average atomic mass. We talked about last week that as we develop this atomic theory, we have to come up with ways to distinguish one atom from another atom. How do we distinguish one atom from another atom? Andrew?
Atomic mass. It's atomic number.
Atomic number, Andrew. And what does the atomic number tell us about an atom, Andrew?
The number of protons.
Number of protons. And that's important because
no two atoms have the same number of protons.
no two kinds of atoms have those same type of protons, okay? But as we get a little bit more sophisticated in our experimentation techniques, gather some more information, we find out about some things called isotopes, right? And we introduced isotopes last week, okay? So isotopes are atoms that have the same number of protons, but different number of neutrons, right? So they are the same kind of element, but they are not the same atom, right? Like Andrew said, number of protons identifies that atom as a certain kind of element. But what we find out is that there are atoms out there that are the same kind of element, but a different atom. They are not the same. So people like Democritus and Dalton that said all the atoms of a certain kind of element are exactly the same, that's not the case, right? So these atoms have the same atomic number, but different mass numbers. And we introduced on Tuesday and Wednesday how if we know the atomic number and we know the mass number, we can figure out how many protons an atom has and how many neutrons and how many electrons. We're going to have to do that a little bit more today. All right, good there? Now, that being the case, we have to come up with a way to distinguish these atoms from one another, these isotopes. Because we can't just say, oh, that's an atom of carbon, because there are several atoms that fit the definition of carbon, 6 protons, but they're not the same. And so we introduced this idea of mass number, right? Mass number telling us the number of protons and the number of neutrons. And we said that mass number is a counting thing, right? Because it's the number of protons and the number of neutrons. Meaning that the mass number, when we write it, is always going to look like what? A whole number, right? Or an integer value. Because it's a counting thing, right? It's the number of protons and the number of neutrons. But if you look at the periodic table, right? Something like this, right? And we look at the numbers on the periodic table, there are some whole numbers, some integer values, but those are those atomic numbers, right? And underneath these numbers, very few of them are even close to whole numbers. So this number here on the periodic table, the other number on the periodic table, right, not the atomic number, like for platinum, this number right here, okay, obviously can't be a mass number. It's got to be something else. And that something else we refer to as the average atomic mass. But first, we have to talk about atomic mass before we talk about average atomic mass. Okay? So write these things down, and then we'll talk about what they mean. So this introduces us to the idea of atomic mass. Atomic mass is a comparison thing, whereas mass number is a counting thing. Atomic mass is used for comparison, used to compare one atom to another atom. Okay? Good there. Catherine, go ahead. AMU generally is lowercase, okay? Although if you write it capital, I probably won't mark off for that. So. All right. Before we get into atomic mass anymore, let's go back to this example that I gave you in class as far as how to make your graph. So up in the top left-hand corner, I wrote down 3 numbers. And these numbers are relative mass factors from your bean lab that you did on Wednesday. Okay? I talked to some of you about this in class. These values are used for comparison, comparing one bean to another kind of bean. Right? So, in the case of my 3 that I have here, which bean am I using as the basis for comparison for all the other beans? Jillian? The navy beans, because what's their relative mass factor? 1. So Jillian, the fact that lima beans have a factor of 5.5, what is that telling you about lima beans? They are about 5.5 times bigger on average than a navy bean is, right? The fact that black beans have a mass factor of 0.9, what is that telling you about black beans? Julie, do you want to answer that one too? Go ahead. About 0.9 times as large as a navy bean, right? So they're a little bit smaller, right? But pretty close, okay? Are we good with that? Right? That's what you did on Wednesday in your lab. You developed a relative mass scale, a relative mass factor to compare all these types of beans to each other. Okay? Good there? That is also what the idea of atomic mass is. Except, not to make your, well, it does make your life more difficult, but the one big difference being, we compared everything to navy beans. And what value did we assign to navy beans on that chart? We assigned that to 1. So it's real kind of easy to compare one to the other, right? Because we're just comparing it to this value of 1. To make your life a little more difficult, atomic mass is not set up off of the basis of 1. It's set up off of the mass of carbon-12, but instead of calling carbon-12 1, we call it 12. Exactly 12. Just like we called the navy bean exactly 1. Okay? Does that make sense? Okay, look good. Because that's to indicate that this atom here, right? Okay, is exactly 12, right? It's got the 4 zeros, but then it's got the dots after it, right? So it's 12.00000000000, right? It's exactly 12, right? And then we compare all the other atoms based off of that value. Okay? All right. So let's look at this here in a little more detail. So here's a chart, and I'm only going to show you a certain part of this chart. This part right here. And this chart compares 2 atoms for us, carbon-12 and carbon-13. But before we can compare carbon-12 and carbon-13, we have to first identify some characteristics of carbon-12 and carbon-13. So, the fact that both of these atoms are carbon should tell you what about them? John? They both have 6 protons. And John, you found that how? Okay, went to the periodic table, found carbon. Carbon's atomic number is 12. Okay, good there? Okay. Oh, sorry, 6. My bad. Okay. All right. Then, the fact that we know that this is the atomic number and it has 6 protons, we can also then tell something else about these atoms, right? What else can we tell about these atoms? Okay.
The number of electrons.
Okay. The number of electrons is going to be what as well?
6.
Okay. It's also going to have 6 electrons because we said the number of electrons and the number of protons has to be the same. Okay. But now, if we do a couple of simple calculations, we can also tell what about these atoms? Rhea?
Number of neutrons.
Number of neutrons. How many neutrons does carbon-12 have, Rhea? It's going to have 6 neutrons, right? And then carbon 13 is going to have 7. Okay, good there? Right. So, now let's talk about atomic mass. So here is the atomic mass for carbon 12. And like I told you before, we have assigned a value exactly equal to 12. All right? Here is the atomic mass of carbon 13. And what do you see about that atomic mass for carbon 13? Rhea, go ahead. It's not exactly 13.0000. It's pretty close, but not exactly, right? So, what does that tell us, maybe, about some of the things that make up atoms? Well, where does most of the mass of our atom come from? The nucleus. And what's in the nucleus? And neutrons, right? Protons and neutrons. And if we count up here, protons and neutrons, we get a total of what? 12. And we assign that value 12, right? But here, we get a total of what? 13, right? Sorry, before I should have done that. So, if this is 12, right, if carbon 12 has 12 protons and neutrons, 6 protons, 6 neutrons, and we assign that a value of 12, that means each proton and neutron probably should contain how much mass? Approximately. What does each proton and neutron count as far as mass goes? 1, right? But then, when we get an actual atom of carbon 13, what we find out is, Rhea, it's not exactly 13. Even though we went up by 1 whole neutron, the mass didn't go up by exactly 1. Does that make sense? You okay with that? So what is that telling you maybe about protons and neutrons? Rhea?
Their value is not equal to 1.
They're not exactly the same, right? They're not exactly the same, okay? This would suggest what about the mass of a neutron versus the mass of a proton? John? Neutrons are a little bit bigger than protons are. That's what this number suggests. Okay? Are we good there? Okay, now let's increase degree of difficulty a little bit. Okay? Underneath that chart of carbon, those carbon atoms, there is another chart that tells you about 3 different atoms of magnesium. So here's what I want you to do first. Before we talk about these numbers, I want you to first identify how many protons, how many neutrons, and how many electrons each of these atoms of magnesium has. All right, so let's take 2 minutes and see if we can get that taken care of quickly. How many protons, how many neutrons, how many electrons do each of these atoms of magnesium have? The fact that they're all magnesium makes this job a little easier, right? So, Omar, just because I saw it, I walked past your paper and I saw that you were right. The fact that it's magnesium, what does that tell you first?
It has 12 protons.
Which one of them has 12 protons?
First one,
All of them have 12 protons, right? Because they're all magnesium, right? And that also means they should have 12 electrons as well, okay? That doesn't change. The one thing that changes, though, is the mass number, right? And the mass number then, Omar, what can we tell about the number of neutrons in this case?
The first one's 12.
First one's 12,
Second one's 13.
13,
And 14.
and 14. Okay? Good there. All right. Now, here's the thing about atomic mass. We said atomic mass is a comparison value, all right? We are comparing everything to the carbon-12 isotope. And on the previous chart, we figured out that carbon-12 has 6 protons, 6 neutrons, and 6 electrons. Good there? Magnesium-24 has how many protons, how many neutrons, how many electrons? How many protons, how many neutrons, how many electrons for magnesium-24? 12, 12, 12, right? Christine, how does that compare to the carbon-12 atom on the previous page?
I don't know.
There's carbon-12, right? Okay? And then there's magnesium-24. How big is magnesium-24 compared to carbon-12? Well, it has twice the number of protons and twice the number of neutrons and twice the number of electrons, right? But when we look at its atomic mass, what do we see? Is it twice as big as carbon-12? Nope. If it was, what would its number be? 24. It's not 24. Why? Just isn't. Right? That's measurement stuff. So, Noor, what does that suggest then about protons and neutrons from carbon to magnesium? Are the protons and neutrons in carbon-12 the same as the protons and neutrons in magnesium-24? Doesn't seem like it, right? So maybe all of our protons and all of our neutrons aren't exactly the same. Does that make sense? Right? Because if they were, we would just double everything and it would give us 24, but it doesn't. Right? Good there. But when we look at these numbers, right, by adding one neutron here, how much do we go up? Pretty close to what? Pretty close to 1, right? And then adding another neutron, we go up by pretty close to another 1, right? These are all very close to whole values. Not exactly, but pretty close, right? Does that make sense? But if you look at the actual periodic table, let's take copper, for example, seeing as how you just used it on your quiz. Oop. When you look at copper, this is copper's atomic number of protons, right? But this number right here, is that close to a whole value? It's right in the middle, right? 63.5. None of those numbers we looked at there were that far away from a whole value. So is that number an atomic mass? Can't be. All of our atomic masses are pretty close to whole numbers, but that one isn't. That number is something different, and we call that number the average atomic mass, which I will get to here in a second. Oh, good Lord. There we go. The average atomic mass. What we find out is in nature, these isotopes, magnesium-24, magnesium-25, and magnesium-26, right? Actually, let's do that. I should have done that. Sorry. If we find magnesium on the periodic table, there's magnesium square on the periodic table. Let me take it and put it on this page. So there's magnesium square on the periodic table. Check out this number, 24.305. Is that the atomic mass of magnesium-24? Is the atomic mass of magnesium-25? Is it the atomic mass of magnesium-26? Not any of those, right? So this number can't be an atomic mass. right? It's, like I just said, because I thought of something as we were talking, right? This is what we call an average atomic mass. What we find out is that while magnesium-24 and magnesium-25 and magnesium-26 all exist, they don't exist in the same proportions. There isn't one magnesium-24 for every one magnesium-25 for every one magnesium-26, okay? So the number on the periodic table, the average atomic mass, has to take into account, well, how many magnesium-24s are there? How many magnesium-25s are there? How many magnesium-26s are there? So that number on the periodic table is not an atomic mass, it's an average atomic mass. It takes into account the atomic mass of each of the individual isotopes, but also how often do they occur, or what we refer to as the relative abundance of those isotopes. We okay with that idea? Let's see what it means. On the back side, there's a couple of pictures here. And I'm going to show you this picture of bromine. Okay. Bromine is a liquid at room temperature, so there's a nice little sample of it here. And if we looked at a random sample of 8 atoms of bromine that show up in that sample, what we would find out is that there are bromine 79 atoms, and there are also bromine 81 atoms. Okay? The fact that they're both bromine should tell you what about them? Andrew?
They're isotopes.
They're isotopes. Do you know anything else more specifically about them? If you looked at your periodic table, you might be able to figure something else out specifically about them. Just for the sake of time, does anybody else have their periodic table out? Anyone find bromine on the periodic table? Nora, did you find it? What you can tell me about bromine, these 2 bromine isotopes?
We have 85 protons.
Okay, both of these bromine isotopes have 35 protons. Okay, but because their mass numbers are different, this one has 44 neutrons, while this one has 46 neutrons. Okay? Good there. What's the average mass of a bromine atom in that sample going to be? Well, how many bromine 79s do you see in this sample? 4. And how many bromine 81s do you see in that sample? 4. So what's the average going to be? Total, and then you divide by 8, right? Now in this case it's easy because we have half of these and half of these, right? So where's the average going to be? Right in the middle, right? So the average atomic mass of bromine is 80. Even though there aren't any atoms that have a mass of 80. Does that make sense? Okay. We'll pick it up here on Monday. There is some stuff I'd like you to read out of your book about average atomic mass and atomic mass. Okay? Check that out. We'll pick it up on Monday.